Hello friends, welcome to the lecture series of Technocrat Group of Institution, Bhopal. I Divya Jain, Associate Professor, Electronics and Communication Department of Technocrat Group of Institute, Bhopal. Today I am going to deliver my lecture on the topic ECG signal analysis using digital signal processing technique. Here are the organization of my lecture, that is introduction, need of ECG signal analysis, what is ECG signal, how ECG signal can be captured, example of ECG signal, parts of ECG signals, step of ECG signal analysis, type of noises in ECG signal, pre-processing of ECG signal, technique for feature extraction from ECG signal, classification technique for ECG signal, and conclusion. So I am going to start my lecture, that is first introduction. The recognition of data from electrocardiogram. Today, the recognition of data from electrocardiogram is the important area of biomedical signal processing. So the identification of ECG signal in real time is closely related to the classification of the patient's diagnosis inspected for the purpose of diagnosis of cardiac status. That means with the help of ECG signal analysis, we can diagnose many of the heart diseases. Here is the need of ECG signal analysis. With the help of analysis of ECG signal, we can check the heart's electrical activity, how fast your heart is beating. Find the cause of unexplained chest pain, which could be caused by heart attack, inflammation of the sac surrounding the heart, or angina. With the help of ECG signal, we can find the cause of symptoms of heart diseases such as shortness of breath, dizziness, fainting, or rapid irregular heartbeats, that is called palpitation. Find out if the walls of heart chambers are too thick, that is called hypertrophied. And with the help of ECG signal analysis, we can also check how well medicines are working and whether they are causing side effects that affect the heart. Check how well mechanical devices that are implanted in the heart, such as pacemaker, are working to control a normal heartbeat. Check the health of heart when other diseases or conditions are present, such as high blood pressure, high cholesterol, cigarette smoking, diabetes, or a family history of early heart diseases. An ECG can also show lack of blood flow in the heart muscles, that is called coronary heart disease, and a heartbeat that's too fast, too slow, or irregular, that is called arrhythmia. An ECG signal can also diagnose a heart that does not pump forcefully enough, that is called heart failure. Heart muscles that's too thick, or parts of heart that is too big, that is called cardiomyopathy. And finally, the ECG signal can detect birth defects in the heart, that is called congenital heart defects, problem with the heart walls, that is called heart wall disease, inflammation of such that surrounds the heart, it is called pericarditis. The test also show how long it takes for electrical signals to travel through the heart. Now before analyzing the ECG signal, we should know what is the ECG signal. The heart cardiac cells are negatively charged. Losing this negativity, this is called depolarization, which is the fundamental electrical activity of the heart. Depolarization propagates from cell to cell, producing a wave. This wave is transmitted to the entire heart, producing a current. This current can be detected using skin electrodes. Skin electrodes are put on the surface of the body, and finally we get the result is periodic signal, that is called ECG. So the electrocardiogram ECG is nothing but a time-varying signal reflecting the ionic current flow, which causes the cardiac fiber to contract and subsequently relax. The surface ECG is obtained by recording the potential difference between the two electrodes placed on the surface of the skin. A single normal cycle of ECG represents the successive artery depolarization or repolarization, and ventricular depolarization and repolarization, which occur with every heartbeat. These cardiac cells can lose their normal negativity in a process called depolarization, which is the fundamental electrical activity of the heart. This depolarization is propagated from the cell to cell, producing a wave of depolarization that can be transmitted across the entire heart. This wave of depolarization produces a flow of electrical current, and it can be detected by keeping the electrodes on the surface of the body. Once the depolarization is complete, the cardiac cells are able to restore their normal polarity by a process called repolarization. This is all the process by which the ECG is generated. How we can capture the ECG signal from a human body? ECG commonly measured via 12 specifically placed leads. It is obtained using 4 limbs leads and chest leads in 6 positions. The right leg is used to place the reference, that is called ground electrode. The left arm, right arm and left leg are used to obtain leads 1, 2 and 3. Electrodes are attached to the chest and limbs to record small voltage changes as potential difference, which is transposed into a visual tracing, that is called ECG. That is an example of ECG signal, and it is the waveform. It is the one cycle of a ECG signal waveform in which we can see different parts of ECG signal, which are the very important part for ECG signal analysis. These are, we can see, that is the P, Q, R, S complex, T peak, there is the PR segment, QRS interval, ST segment. All these parts are very important for analysis of ECG signal by which we can diagnose any disease. Here I am discussing about all the parts of ECG signal. First is P wave. P wave indicates atrial depolarization and contraction. Its relation between P and QRS helps distinguish various cardiac arrhythmias. Shape and duration of P wave indicate atrial enlargement, and QRS wave, complex wave, is QRS interval includes 3 deflection following P wave, which indicate ventricular depolarization and contraction. Q wave is the first negative deflection, while R wave is the first positive deflection. S wave indicate the first negative deflection after R wave. Represent ventricular depolarization. The QRS complex represents ventricular decomposition, larger than P wave because of greater muscle mass of ventricles. And the QRS wave, the duration of QRS wave is 0.08 to 0.12 seconds. Its duration, amplitude, morphology are useful in diagnosing cardiac arrhythmias, ventricular hypertrophy, MI, electrolyte derangement, etc. Q wave greater than 1/3 the height of R wave, greater than 0.04 seconds are abnormal and may represent MI. The PR interval shows, in the PR interval measure time during which a depolarization wave travels from the artery to the ventricles. The normal duration of PR interval is 0.12 to 2 seconds, that is 120 to 200 milliseconds, or 3 to 4 horizontal boxes on the ECG graph. It is from onset of P wave to onset of P wave to onset of QRS wave. Prolonged PR interval may indicate a first degree heart block. ST segment. The ST segment measures the time between the ventricular depolarization and beginning of repolarization. Connect the QRS complex. The ST segment connects the QRS complex and T waves. The duration of ST segment is 0.08 to 0.12 seconds, that is 80 to 120 milliseconds. The T wave represent repolarization or recovery of ventricles. The interval of T wave from beginning of QRS to apex of T is referred to as absolute refractory period. The QT interval represent total ventricular activity measured from beginning of QRS to the end of T wave. Normal QT is usually about 0.4 seconds. The normal QT interval is usually about 0.4 seconds. QT interval varies based on heart rate. These are the steps for ECG signal analysis, in which we analyze all these intervals and feature extraction are there. The method used for diagnosis generally involve four essential processes to arrive at the accurate and quick decision about the kind of heart disease a patient suffers from. It includes first is data acquisition, in which we acquire the data from the ECG machine, denoising or pre-processing. In this step, we remove the noise in the ECG signal, feature extraction, in which we extract the features like the intervals, the peaks and all these things. In the next slides we discussed about the features which we extract, and last is the classification, by which we check the acquired ECG signal is normal or abnormal. ECG signal processing. In order to extract useful information from the noisy ECG signal, we need to process the raw ECG signal. The ECG signal processing can be roughly divided into two stages by functionality. First is pre-processing and second is feature extraction. The pre-processing stage removes or suppresses noise from the raw ECG signal. Feature extraction stage extracts diagnostic information from the ECG signal. There are some noises which occur in ECG signal for which we have to do pre-processing. First is power line interference. It is a significant source of noise. Data cables carrying ECG signal from patients to display devices are influenced by electromagnetic interference (EMI) from the 50 to 60 Hz power line noise. This noise degrades the signal quality and affects the tiny features which can be critical for clinical diagnosis, monitoring and signal processing. The next noise is baseline drift. The baseline drift can be represented as a sinusoidal component at the frequency of representation added to the ECG signal. It is usually from respiration with amplitude of about 5% at frequencies drifting between 0.15 and 0.3 Hz. The drift causes problem in the detection of ECG signal, that is, sometimes the amplitude of T wave is higher than the peak of R wave and results in false detection of R peak. And the next one is motion artifacts. Motion artifacts are due to either the patient's movement or loss of electrode contacts. Transient baseline changes caused by alteration in the electrode skin impedance with electrode motion. And the next is electromyographic interference. It is due to muscle contraction and transient variance and duration of burst. It usually lasts around 50 milliseconds between DC and 10,000 Hz with amplitude of 10% level. And the last one is the composite noise. The composite noise means a combination of all noises mentioned above, and instrumentation noise and electro-surgical noise. All these are the composite noise. The removal of power line interference. Here we are doing the pre-processing of all the noise which we have discussed in the previous slides. For removal of power line interference, we use the low pass filter. The noise for processing of removal of power line interference, here we are using low pass filter. The noise is ergodic process, can be suppressed using temporal statics in place of ensemble statics. In this process, a few samples are used to obtain output at various point of time using moving average filter. The moving average filter is also called one-horn filter or low pass filter. The general formulation of moving average filter is, that is, output Yn is equal to the summation of k is equal to 0 to n Ck xn minus k, where xn is the input and yn is the output respectively, and Ck values are weight coefficients. Taking the z transform of above equation, we get the transfer function Sz, that is C0 plus C1z plus C2z raised to the power minus 2 up to Cn z raised to the power minus n. The simple averaging filter derived from equation 1 is given by Yn k xn plus 2 xn minus 1 plus xn minus 2. Here we are taking the 4 points and taking average of these 4 points, where k is gain. Taking the z transform, we get yz is equal to k xz plus 2z inverse xz plus z raised to the power minus 2 xz. So the transfer function hz is equal to k into 1 plus 2z inverse plus z raised to the power minus 2. At z is equal to 1, normalizing gain is 1. Therefore, finally the low pass filter response is 1 by 4 plus into 1 plus 2z inverse plus z raised to the power minus 2. When we pass our ECG signal from this low pass filter, we get the result. Here we can see the high frequency noise is removed and only the low frequency signals are passed. And here the power spectral density of the actual ECG signal, which is the acquired, and the low pass filtered ECG signal, the difference is here that the high frequencies are removed, which are the noise signals. Here is the power spectral density of original signal at 60 Hz peak due to power line interferences observed. After low pass filtering, ECG signal is passed through a derivative filter. So we are using derivative filter for removal of baseline inverter. The derivative filter, as its name suggested, take the derivative of the signal. For constant signal derivative is 0. For constant signal derivative is 0 because the baseline drift is due to the DC signal, which will shift the level of ECG signal. For that ECG signal removal, we are using derivative filter. The derivative is higher where signal is changing abruptly. Mathematically, derivative filter is defined as yn is equal to 1 by t xn minus 1. That is, we are taking the difference between two adjacent samples. After taking z transform, we get hz is equal to 1 by t into 1 minus z inverse. That is the transfer function of the derivative filter. However, to remove baseline wonder, a careful design is necessary, as filtering can distort QRS complex. To reject DC component, a 0 at z is equal to 1 is desirable, but we also want to retain components whose frequency is more than 0.5 Hz and gain of the filter should be very close to unity for frequencies greater than 0.5 Hz. In Z plane, poles can only be placed inside the circuit due to stability criteria. Moreover, to attain higher gain at very low frequencies, poles should be on x-axis, that is at 0 frequency and close to 1. Therefore, it is considerable to be at 0.995. So, after putting all these conditions, we get the transfer function, that is hz is equal to g by t into 1 minus z inverse divided by 1 minus 0.995 z inverse. Here we are taking the pole at 0.995. And considering t is equal to 1 and unity gain at z is equal to minus 1, we get the final transfer function for derivative filter is 0.9975 into 1 minus z inverse divided by 1 minus 0.995 into z inverse. After passing our ECG signal from this derivative filter, we get the result that after filtering the original signal and after passing the derivative filter, the result is there, and the power spectral density is shown here of the original ECG signal and derivative filter ECG signal. After that, we are using notch filtering for removing the 60 Hz noise. Notch filter can be used to remove certain frequency component which are undesirable for placing zeros at those locations. The radius of zeros should be equal to unity, while angles of zeros should be at plus minus f0 by fs into 2 pi, where f0 is the frequency and fs is the sampling frequency. Z1 is the first zero at e to the power minus j ohm 0 and Z2 is the second zero at e to the power minus j ohm 0. So the transfer function is z minus z1 into z minus z2 by z square for notch filter. In case where if we are taking sampling frequency 200 Hz and the frequency which we want to remove is 60 Hz, that is f0. Therefore, we get the final transfer function for notch filter is Z square minus 0.618Z plus 1 divided by Z square. So here we are seeing, here we can see the original signal and filtered ECG signal after passing the notch filter, and the power spectral density of original signal and notch filtered ECG signal. Here the 60 Hz noise is removed. We can use all these filters in the cascade form. First we are taking low pass filter, after that derivative filter. With the help of low pass filter we have removed the high frequency noise. With the help of derivative filter we are removing the DC line or baseline wander, and with the help of notch filter we have removed 60 Hz noise. So we can take all these filters in the cascade form and remove all these noise. The final transfer function of cascaded filter is transfer function of low pass filter into transfer function of derivative filter into transfer function of notch filter into the transfer function of input signals. So after passing the original ECG signal from these cascaded filter, the result, here we are showing the result. After passing this cascaded filter, the power spectral density shows that in the original signal the high frequency noises and the 60 Hz noise and baseline wanders are there, but after passing from the cascade filter all these type of noises are removed. Here the pre-processing steps are complete. After completing the pre-processing step, we can do the feature extraction. The feature extraction techniques involve statical feature extraction. In statical feature extraction, mean, mode, median, standard deviation are first order statical features. Variance, kurtosis, skewness are higher order statical features of ECG signal. Standard deviation gives the measure to quantity the amount of variation or dispersion of set of data values. Kurtosis is a measure of whether the data are peaked or flat relative to a normal distribution. Data with high kurtosis tend to have a distinct peak near the mean, decline rather rapidly and have heavy tails. Skewness indicate asymmetry and derivation in distribution analysis from a normal distribution. After that, in the feature extraction, the morphological feature extraction, the feature extraction stage extract diagnosis information from the ECG signal. The detection of R peak is the first step of feature extraction. The R peak in the signal has the largest amplitude among all the wave composed compared to the other leads. Pan-Tompkins algorithm can be used to detect the RR interval of ECG signal. Next one is the transform-based feature extraction. In the transform-based feature extraction, ECG signal, because the ECG signal are in time domain in their raw format, the pathological conditions, however, may not always be quite obvious in the original time domain signal. These conditions can sometimes be diagnosed more easily when the frequency content of the signal are analyzed in the frequency domain. So in transform-based feature extraction, we first convert the ECG signal from time domain to the frequency domain, and different type of transform we can use for transform-based feature extraction. For transform-based feature extraction, we can use fast Fourier transform. Earlier, the method used for ECG signal analysis was time domain method, but the limitation was that it was not sufficient to study all characteristics of ECG signal. So a new method, FFT, was developed. Fourier transform is a well-known method which transform time domain signal to frequency domain to obtain frequency coefficient. Next one is the short time Fourier transform, STFT. To overcome the shortcoming of FFT, Dennis Gerber in 1946 first introduced the windowed Fourier transform, that is short time Fourier transform, known as Gerber transform. And the next one, next is STFT has both time and frequency information. It is used to determine the sinusoidal frequency and frequency content of the signal, as it varies with time. The STFT-based spectrum is a simple and fast technique in comparison to other time frequency analysis. Next technique for feature extraction is wavelet transform. In STFT, windows should always have fixed size, and thus it does not give multi-resolution information of the signal. But wavelet transform has the multi-resolution property which give both time and frequency information through variable window size. In contrast to conventional techniques, the wavelet transform provides a new dimension to signal processing and event detection due to its time frequency localization properties. The wavelet transform is an efficient tool for analyzing non-stationary ECG signal. The wavelet technique provides a description of a signal in time scale domain, analogous to time frequency domain, allowing the representation of temporal features at multiple resolutions. This is achieved by the decomposition of the signal over dial, scale and translated time various of a prototype wavelet. It is continuous from the WT of a signal. It is continuous form of WT signal. Now after pre-processing and feature extraction, we use the classification of signal for detecting abnormalities in the ECG signal. Classification of heart rate is based on neural network and fuzzy. That is, heart rate is classified by using heart rate variability, that is HRV. Some features are extracted from this HRV and it is given as an input to the neural network. And fuzzy, equivalence for classification. Now, after classification, we can differentiate the ECG waveform into normal and abnormal by using features, and it is given to the input of the classification. The classification can be performed by linear discriminant analysis (LDA) and artificial neural network (ANN). In this, multi-layer perception was carried out in ANN. After the classification, we can detect that the acquired ECG signal is normal or abnormal, whether there are some disease are present or not. Software used for ECG signal processing and analysis. We can analyze a ECG signal by using the most familiar and multi-purpose MATLAB software along with learning. The proper utilization of MATLAB functions, both built-in and user-defined, toolbox and Simulink can lead us to work with ECG signal for pre-processing and analysis, both in real time and by simulation with great accuracy and convenience. Now the conclusion is that in this presentation we have discussed various ECG signal processing techniques. ECG signal processing techniques are helpful to diagnose several heart diseases. Thank you.